everyone, and welcome to Vedanta Aluminium Presents Masterclass on the Metallurgy of Extrusion powered by Pro MFG Media. Vedanta Aluminium is India's largest producer of aluminium and value-added products. It is also the largest manufacturer and exporter of high-quality aluminium billets, which finds usage in building and construction, solar renewable energy, automotive, electrical, and many other core industries. The inherent unique properties of aluminium can be leveraged well by the versatility of the extrusion process. This makes the aluminium extrusion sector a unique industry with specialized requirements. To have a competitive edge in this sector, extruders need to deliver excellent results in terms of speed and quality while also focusing on productivity. In today's masterclass, we have industry leaders and technical experts from Vedanta joining us to share valuable insights which will help extruders improve productivity while delivering speed, strength, and quality. We have received many questions from our audience and we will be addressing them live. During the masterclass, if you have any questions, kindly post them in the Q&A box. There is a lucky draw at the end of the session, so kindly be present till the end. I would now like to introduce Mr. Alok Ranjan, Chief Marketing Officer, Aluminium Business, Vedanta Limited, and invite him for the opening address for today's session. A brief introduction: he's an industry stalwart with over 20 years of experience in the metals and mining sector across multiple commodities. A warm welcome, and over to you, Alok.
Thank you, Ramya. So a really very warm welcome to all the participants, all the audiences who have joined today, who have taken some time out of their busy schedule, and I'm sure you'll be benefited by this session. I also extend very warm greetings to my fellow panelist, Ram, who leads the customer technical services in Vedanta Aluminium, and our expert for today, Mr. Jonathan Pangborn. So Johnny is an old advisor for us and works very closely with us on various matters. He's a technical expert, and I hope that you'll all benefit with the interaction today. And I welcome you to participate and ask questions, because the more you ask questions, the more we understand you and more we tailor make our product and give you better services. Going forward, we'll ensure that we continue to have sessions like these on a regular basis. And this is just the beginning. And in future, we'll have separate sessions on more technical aspects of our products in billets or PFA or wire rods. We want to make this a regular feature, and we welcome you to participate and make this session quite engaging. So I'll spend next few minutes talking about Vedanta, and then I'll hand over the reins to Ram and Johnny in particular, who will take you through the session for today. So moving on. Yeah, so most of you would know Vedanta is a very large natural resources conglomerate. We are around 6th or 7th largest in the world. We have interest in aluminum, copper, zinc, lead, silver, oil and gas, and commercial power, and operations are spread across India and Africa. And in all the businesses wherever we operate, we are among the largest in the world. So we are probably 2nd largest zinc producer in the world. In aluminium, today we are 6th largest. However, we are en route to become 2nd largest or 3rd largest, depending upon how peers perform. We'll be the 2nd or 3rd largest aluminium producer in the world outside of China. Similarly, in copper and oil and gas, we produce 25% of India's private sector production. And we have massive growth plans in wherever. I mean, in all the businesses, we are in the midst of close to $20 billion worth of investment, which will make us one of the largest natural resources company with a targeted revenue of around $50 billion. Moving on. So again, Vedanta is a company not only engaged in metals and mining, but we have a larger purpose. And the larger objective or the purpose of this organization is to serve the communities where we operate, to serve the stakeholders, be it investor or the government or the employees. And by way of, we are a metals and mining company, so we consistently want to leverage the natural resources which India is endowed with, focus a lot on research and development, acquire sustainable assets and develop them further. So that has been the core mantra of our growth throughout the last few years. Moving on. So a little bit about our Vedanta Aluminium business, the company which I represent, and today we are focusing more on aluminium. We are why Vedanta? So if you, some of the key things which differentiate us from others, fellow peers, is that we are very large conglomerate. We are the experts in whatever we do. And we do that by leveraging best-in-class industry technology, innovating consistently, and digitalizing whatever operation we have. So today, you will be happy to know that one of the best and most advanced mining mines are being operated in India under Hindustan Zinc. And that has been done because of the consistent focus on being ahead of the curve, which we have. Very quickly, I'll talk about the aluminium assets. I think we all know aluminium is a metal of the future because it's highly sustainable, it is infinitely recyclable, and it is highly versatile and dynamic, and it can be used. Aluminium today can be used to replace any other metal like steel, copper, wood, glass, plastic. So that's the diversity of versatility of aluminium, because it can be used in multiple applications. Now, in aluminium business, we have alumina refinery in Odisha, and we operate 3 smelters, 2 in Jharsuguda, which is in again Odisha, and 1 in Korba. So total installed capacity is around 2.3 million tons. But I just said we are on our way to expand that capacity to close to 3 million tons. So this expansion will come in Korba, Chhattisgarh. Moving on. So this is the location of the asset, which I already discussed. Some of the bullet points, I mean, not talking about the product, which my colleagues will address in subsequent slides, but something which we are really very proud of is the impact which we have. Now, we employ close to 26,000 people, directly or indirectly. And again, we impact the lives of close to 5 lakh people around the operations wherever we operate. So we directly or indirectly touch lives of 5 lakh people. So we really feel proud of the impact which we are having on the community which we operate. Moving on. So again, one of the key messages or key differentiator today for any resources company is that how sustainable we are. I mean, today, the biggest challenge which any natural resources company is facing is about intergenerational equity. I mean, we operate in non-renewable resources, which means that it will deplete, it is not going to last forever. So how do we develop resources in a way that the generations to come are not adversely impacted by that? So there's a huge focus on that, and we take a lot of pride in that, because I mean, some of the highlights which separates us is that we are one of the largest renewable energy buyer. So for instance, we bought close to 3 billion units of renewable energy last financial year. We recycled 15 billion liters of water. Almost everything whatever we produce is recycled, reused. So there's nothing called waste. So we have a program called Wealth from Waste, and we ensure that whatever we produce, nothing goes waste, and we extract everything, every value out of whatever we operate upon. And again, similarly, in the similar vein, we were able to conserve close to 1.33 million gigajoules of energy last year. So that just speaks about the focus which we have on sustainability. Now, I already spoke about the social impact. Another marquee feature which we have is that when we talk about inclusion and diversity, it's not just many companies who are taking steps. They talk about gender diversity, but we have gone ahead and we have, genders, all genders. So now some of the transgenders also are very comfortably assimilated in our family, and they are working under various roles. So again, this just goes to show that sustainability or ESG is not a mantra, just not a buzzword for us, but it is at the core, it is at the heart of our entire strategy, and we really take pride in whatever we do. So with this, I'd like to hand over the session to Ramya, who can then take this session forward. Thank you.
Thank you, Alok. Now, to take the proceedings further, I would like to invite Mr. Ram Adhikari, Head Customer Technical Service, Aluminium Business, Vedanta Limited. Ram heads a very critical function of customer technical service, which collaborates with customers to provide the best technical solutions to them as part of Vedanta's value-added service offering. Welcome, Ram, and over to you.
Thank you, Ramma. First of all, I would like to welcome all the participants of this masterclass, and I would like to thank Johnny for allowing his presence and delivering this insightful session with us. I shall be sharing a small deck with which will encompass how Vedanta is positioned its product portfolio, the value chain, and the facility update that we have. So, aluminum is a alloy of element of unique proportion. It has got its very high weight to strength ratio, very high corrosion resistance, and it is very superior towards electric conductivity. So weighing everything, now aluminum can be used everywhere. It can be used in aerospace, airplane, rocket, missiles. It can be used in automobile sector, electrical segment, the EV segment, everywhere this can be used. So this is of course there. Just taking it forward, this we are doing it, selling this our product to 50 plus countries, which encompasses all the American continents, Europe, Oceania, and Middle East and Africa. Our products, typically we supply our products into various forms and factors, and it starts with wire rod, billet, foundry alloys, of course, remelt products, and all these products are going into different applications. The form factors and the process of these products depends on what is the end product is. And as I've already discussed, it can range from going into aerospace to automobile to electrical segment everywhere. Again, talking more about the sustainable footprint of Vedanta, we have launched two products. One is Ristora, another one is Ristora Ultra. Ristora is an aluminum product which is being produced by using renewable energy, which has a GHG emission of 4 tons per CO2. And Ristora Ultra is the ultra low variety of it, which has near zero carbon footprint, and it has been produced in collaboration with Runaya. Again, this is a testimony of our zero waste or waste weight culture that we are driving. Talking about value chain, our value chain begins with bauxite mining, then it goes to alumina refinery, where bauxite to alumina transformation takes place. Then it comes to our smelters at Jharsuguda as well as into the Korba, Chhattisgarh. And in the smelter, we electro-refine this alumina to aluminium. This aluminium then transferred to our cast houses, where again this took various form factors before finding its in applications in almost every aspect of our life. Talking more about the technologies that we deploy, it starts on the state of the technology, and these technologies majorly come from USA, Austria, China, and Italy. So these are the typical production system that we deploy, and we have our laboratory which is accredited with NABL accreditation, and we have all the state-of-the-art facilities to make sure that our product stands out with respect to its quality performance. Talking about quality again, we are certified with integrated management system, which encompasses ISO 9001 for quality, 14001 for sustainability, as well as 45001 for the safety. We are also certified with International Automotive Task Force, IATF 16949, which majorly talks about the automobile requirement and how do we comply to those. Recently, we got our 15 products certified with the BIS certification as well. So on the quality and sustainability standpoint, these are the few certificates that we have. Talking about the customer service, we collaborate with customer to develop new product as well as to support them with how they can improve onto their production process, their efficiency. We have our global expertise technical service panel who engage with customer and make sure they are getting the right input to not only get the right product quality, but to improve on the overall journey that we have. We also work on the market development, and we also work on the customer devices if there are any. Now, talking more on the today's subject matter, that is billet. We are offering billet with respect to the state of the technology. We use wax trap technology, which uses hot tub airship casting. and hot pitch continuous homogenizing furnace as well as blast furnace. Currently, we are at 460 KT operating capacity, which we are ramping up to 1.2 million. And currently, we offer diameter ranging from 6 inch to 10 inch. I am very pleased to inform you that we have commissioned another 120 KT billet feed, which will offer 12-inch press size as well, diameter as well. And we are in process to get another set of table for 5-inch, which will be commissioned by FY24. Now, I would like to present to you a short film about our offering to the extrusion market.
Thank you for the interesting video, Ram. We are all set to begin with the masterclass, for which I would like to invite Mr. Jonathan Pangborn, the global extrusion expert and technical advisor, Billet Extrusion, Vedanta Limited, Vedanta Aluminium. Mr. Pangborn is a knowledge consultant in extrusion casting, surface finishing, and managing of machining of aluminium alloys, having over 2 decades of experience. He's joining us from the USA. Over to you, Mr. Pangborn, as our audience is keenly waiting for today's masterclass on the metallurgy of extrusion.
Unmute here. Very excited to be with you today and talk about one of my favorite subjects, metallurgy of extrusion. This is near and dear to my heart, as Ramya had said, had several decades in this industry, and I really enjoy it, and it really makes a difference for people's lives. Let me present. There we are. So thank you again. We'll get started here. So this is an outline of the topics we're going to be looking at today. General overview of the extrusion process. We won't be getting in too much detail, but talking to it with regards to the context of the metallurgy, building up to the importance of that and how we need to control that in our facilities. some fundamental concepts around that, some definitions, and looking a little more into detail into the design and the purposes and the definitions of these process steps. And really that's where we'll get into the meat of the metallurgy. And then we'll close with some future trends, what's coming later. Extrusion process, first of all, there are several extrusion methods that we'll briefly outline, talk about some basic terminology so we all have the same understanding of that. And then dive into the process steps, the why and how of what we do, specifically addressing the need for good temperature control and presenting extrusion as a heat treatment process. And really, in light of that, we're primarily talking about 6,000 alloys, although many of the topics that we're going would apply to all different types of products. So here are the three different methods of extrusion that we're going to cover. First is direct extrusion, which is by far the most common, where the stem or the ram moves and pushes the billet through the container and out through a die in the same direction. Indirect extrusion. There we are. There's a sealing element, a container that move together over the die. So actually the die is moving in the opposite direction of the extrusion, and the die is on the end of a hollow stem or ram. And then seamless extrusion, which can be applied to either of these, and the direction's a little bit different for this particular diagram, but the stem is moving from right to left, but there is a mandrel extending off the stem that is causing the hollow element within the die. And in this process, there is no seam, there is no weld, for example, as we would see in a porthole die. For the purposes of this discussion, we'll be focusing on direct extrusion, as I said, of 6,000 alloys. And really because that is the most common and the most relevant to us. But again, most of the different topics we're going to be talking about, the different components of the discussion are going to be similar to other alloys for direct extrusion and also to indirect extrusion and even other materials. But as we go through this, we're really framing the discussion for more details later when we're talking specifically about the metallurgical aspects. So here we have an overview of an extrusion press schematic here. Fundamentally, an extrusion press is a very large hydraulic cylinder, very commonly in the 1,000 to 10,000 ton range, although there are certainly larger and smaller ones than that. But the aluminum or aluminium is enclosed here in this container. Hopefully you can see my pointer. And the billet is being pushed, as we saw in the other diagram, direct extrusion by the ram through a die. And then there's various other components that are around this that kind of hold it together. We have support for the tooling. We have a front platen that supports all that tooling and the massive forces that are being produced here. And that is tied back by a press column, or also known as tie rods, back to the back end. So the force is proceeding in this way. And I do want to emphasize this is a solid state process. Extrusion, unless you do something unfortunate, you do not have molten aluminum. It is a solid state process. So even the welding through the porthole dies, that is a solid state welding. There's no fusion welding as you'd have with a typical joining process. So here's another way to look at extrusion. What are the elements that are leading through the process? We have these main inputs here. Of course, we have the billet or the log, the raw material. We would be purchasing dies and hiring people and employing energy, electrical and gas primarily, as the main inputs, and we would put those into the core processes. We're going to preheat the billet and extrude, and then ultimately cool the product. And then we'll follow that with various handling. We're gonna stretch, cut, and rack there through the handling system, process our material into a more usable form, and then finally, depending on the needs of the customer, we have various finishing processes. Aging would be used for nearly all 6,000 alloys. Some of our products are fabricated or surface finished, painted, anodized, and for all kinds of different markets, right? Different applications. Automotive is certainly a growing sector. Building and construction has been common for many decades, but has continued to grow. There's many general fabrications and industrial products, as well as other special usages, electronics, aerospace, electrical transmission, many other applications for aluminum extrusions. So we're going to show a quick video, and some of this may be familiar for those of you in extrusion plants, but this is a very good video that outlines what we're talking about before we continue deeper into the metallurgy.
Specified aluminum alloy cast in log form and pre-cut to uniform length is known as a billet and is first placed into the billet furnace, where it's heated to almost 900 degrees Fahrenheit. The billet then exits the furnace and is transferred to the extrusion press. The excess material from the previously loaded billet is sheared, and a ram pushes the new billet through the container and extrusion press using thousands of tons of hydraulic force. The soft aluminum is pushed through the steel die opening to create a fully formed profile. As the formed profile exits the extrusion press, it is cooled in a water bath. This is called quenching and is done to uniformly cool the extrusion at a controlled rate to establish intended mechanical properties. A device called a puller grabs and secures the hot extruded length and guides the profiles down the runout table. The puller and runout table, a sophisticated mechanical process that uses conveyors and belt systems, is synchronized to the speed of the extrusion press. Let's take a closer look at the importance of temperature and process controls throughout the extrusion run. Controlling the heat of the alloyed aluminum as it moves through production is a critical success factor that requires a number of variables to continuously align with one another. We've already discussed the heating of the billet to a malleable temperature, but you should also know that the container, extrusion die, and other support tooling are also preheated to temperatures that allow the aluminum operating temperature to be maintained at desired levels throughout each push. If these process components aren't precisely controlled within their specified temperature ranges, the operating temperature of the aluminum will be impacted by those components, either by adding to or absorbing from heat required for solution heat treatment.
There we go. Excellent video there, and it shows the process, and it also leads into where we're going next, which is really going to be pretty deep into the temperature control and how important that is in the process. Next slide. Here we go. First of all, some definitions or fundamental concepts I wanted to outline. First, strength. That's a very simple concept, but really what we're talking about is resistance to deformation. So in the aluminum, we're applying a force. How much force does it take to deform that? Temperature, of course, very basic concept, but really what defines temperature is the movement of atoms, how rapidly and to what degree they're vibrating within us, within the table in front of us within the aluminum that we're processing. And that has a big effect for us as we talk about time and temperature, because the temperature changing allows things to happen more quickly or more slowly. And we'll talk about that. Briefly mention what's called the crystal lattice, which is the atomic arrangement of aluminum in the alloys. In this case, 6000 series alloys that we're talking about. We will briefly be looking at some graphics for that. Solution. This is an important concept. Basically, like you have hot tea and you put sugar in it, you are dissolving the sugar. In a similar manner, when we change the times and temperatures, we are solutionizing our metal, so that for 6000 alloys, magnesium and silicon, the primary alloying elements, we're dissolving those in the base aluminum, and we have a solution that, at least from a high level, is indistinguishable from the base. We'll contrast that a little bit with hardening phases, which are actually distinct particles that come out of solution. And in our case, again, magnesium and silicon particles, and we control those in a way that strengthens the alloy. So hardening particles, these are magnesium and silicon particles at longer times and temperatures. As the particles grow, they will become Mg2Si, but there are many other phases that are in the spectrum. This is, again, highly sensitive to temperature and time control. Again, remember, the definition of temperature is how active any molecules or how the atoms are moving. So I'll show a little graphic here. On the left-hand side here, let's imagine we're looking through a microscope at the microstructure, we call it, of the aluminum, and we see little or no magnesium and silicon particles. If we are out of control, what very often happens is we get an equilibrium Mg2Si phases, and we'll get few of them, and there will not be very many. And these have very little positive effect on strength. Contrasted with, on the right here, if we were to take the same amount of magnesium and silicon and control how that comes out in the matrix of the aluminum, we would have many fine particles. And this is much more effective for strengthening. This is actually what we're trying to accomplish in aging, which we're not going to talk too much about, really. But in the extrusion process, what we're trying to do is maintain this. And we're trying to avoid having these large particles come out, which are then unavailable for hardening, for forming small phases in the aging. So again, we want to control how this comes out and not let the process just happen to us, but we take control. So looking at, this is the crystal lattice we spoke of here. This particular example is calling out copper atoms, so it's for a 2000 alloy, but it's exactly analogous to what we're talking about, where we have the solvent. It's primarily aluminum alloys in this lattice, and our alloying elements are mixed within, and from a distance, they're indistinguishable, and everything fits. A particle, on the other hand, is something that is distinct and different. It is not in solution, but it is a distinct component. So in this example, these copper atoms, for us, it would be magnesium and silicon for 6000. They begin to come closer together, which is much easier to happen at higher temperatures. Things can happen more quickly and form a distinct particle that no longer fits in this crystal lattice. So you can see in this schematic, these lines are no longer straight. And that is going to increase the strength, as it will be harder to deform the structure. So when a force is applied, the material will not move the same way it did before, and this particle is providing strength. And then ultimately, you have more distinct particles as they grow larger. And eventually, if they grow large enough, you really don't have that many relative to the small ones, and so you're not adding that much strength. What does this actually look like at extrusion? Well, here we have a schematic that's showing our process as we heat up through extrusion. Of course, we're starting at ambient temperature. We are coming up through temperature, we're extruding, and then we're cooling down. So we'll focus on that. We have Celsius and Fahrenheit on this, but in this range here, from about 250 to about 500 Celsius, this is what we call a critical range, and this is really important. First of all, because we have to deal with this. We cannot avoid this or pretend it doesn't exist, because our process is proceeding first up through and then down again through this critical range. So, well, let's pull up a phase diagram, and this is really just a graphical representation of this one's generic, but as temperature rises and concentration increases. So for us, magnesium and silicon increases, the transitions between different components change. So up here in this example, we would have liquid. As we bring temperature down, we begin to freeze. Most alloys will not have a specific melting point. They'll have a melting range. If we were to have pure aluminum, there would be a single melting point, but we have a range here. We go across what's called the liquidus, above which everything is liquid. Here, we begin to have a mushy state, and then at some temperature, relative, for that particular alloy, we have a full solid, and that's what's called the solidus. And that's very, very important, that differential in that range for the casting process. For us, we want to stay below that. Again, we don't want to have any liquid aluminum in our extrusion process. As we continue to drop, we eventually reach what's called the solvus. And in between here, this is where the material is solutionized. Excuse me. So we have a mixture of aluminum with the magnesium and silicon predominantly dissolved in there. And then as we come down through here, in this region here, the magnesium and silicon particles begin to form. So basically, this solvus temperature is what is, go back to this other slide here, come on. What is defining this top of this critical range. And the lower is really defined by the time it takes. It's not that at the lower temperatures, the precipitation of these hardening phases doesn't want to happen. It just happens more slowly. So this has been chosen to be defined as kind of a critical range. In aging, we use much, much longer times, hours, to get the particles, and we're outside this critical range. And that's what we ultimately want to achieve at the end. So we have some strengthening from the magnesium and silicon in solid solution, but in aging, we're increasing that by controlling and having these really fine particles that we want. So in extrusion, I kind of mentioned it, but specifically the goal in extrusion is to keep those hardening elements, magnesium and silicon, in solution so that we can age later. So going through these temperature ranges, and again, with the example of sugar in coffee or tea or hot water being dissolved, and then at a lower temperature, you're not able to dissolve as much. So looking more specifically at the extrusion process itself, we have our preheating step where we're going up to that critical temperature range. Of course, we need to do that. We need to have a softer alloy that we can push through the die and do that reliably. But we also need to control it in a way that we get the final product that we want. And in light of what we're talking about, particularly the property control or mechanical properties that we need by controlling how we go through that critical temperature range. Extrusion, of course, this is our main forming process. We have the heated billet. We're pushing it through the die that we chose to produce something for our customer. But it's really important to control this and make sure that we're well above the temperatures that are critical. So the 500 C range that we threw out there is the high end of the critical temperature range, because actually some particles will begin to form in preheating that we do not want, some large Mg2Si particles, but in extrusion we have the opportunity to absorb that. And then finally, cooling. Of course, we need to cool our material, and again, we're going to choose how we do that. We're coming down through that critical temperature range, so we want to get through it fairly quickly. Billet preheating, the temperature is going to vary depending on the product and what we're trying to accomplish. Many factors here that I will not read, but generally speaking, quite broadly, here is a temperature range that we would normally be extruding at for 6,000 alloys. And there will be exceptions to that, but that's kind of a good ballpark. One of the more important points, I think, is that we don't want to hang out at the lower end of these temperatures, because we're within, or at least very close to, that critical temperature range. So we want to have a stable operation where we're not just having metal stay at temperature. And we certainly don't want to just leave a preheater on for extended period of times if we're not producing. Extrusion is our main forming process, but it is actually a heat treatment process as well. And really the feedback we get for that is the exit temperature. So here in this schematic, we have metal coming through a die through the press platen. And at some distance, we're able to affix an infrared camera and get a reading on the exit temperature. There are other methods we can directly measure with a thermocouple wand or something like that. But this is a critical control parameter for everyone in the extrusion business, because we are intending to solutionize the magnesium and silicon in extrusion. So we're actually doing a solutionizing heat treatment in this process. And of course, we can use this as feedback for maximizing our extrusion speed while maintaining or actually very often improving our quality as we increase speed. Exit temperature is not set. It's a resultant of other parameters. There are some software packages and so forth that will provide feedback from the exit temperature, and you can set what range you want, and it will change your parameters to achieve that. But really, it's your extrusion speed and billet temperature are the main variables at the press that are controlling that, combined with the other aspects that are more fixed. Remember that we have a very massive hydraulic cylinder, thousands of tons of force. Most of that force, that energy, is being converted into heat. So there is a lot of heat generation in the process. So for example, if we're typically running a billet at, I think in Fahrenheit more, but let's say it's at 470 Celsius, we may see an exit temperature of 520 Celsius, meaning we actually heated our metal up 50 degrees Celsius during the extrusion process. That would be fairly typical. I will say that generally the exit temperature should be well above the critical range. I would aim for at least 540 for 6,000 alloys, with the reason being that we're improving our heat treatment process. We're well above the critical range, and we're more easily able to absorb particles that are coming out in that preheating. Cooling, it's necessary, of course, to control. We're coming back through that critical temperature range. Cooling rate that's required is going to be highly dependent on what alloy we're extruding, and there may be some variations depending on the mechanical property requirements. Most of what we extrude, if we're a facility that extrudes, for example, out of 6063, we may primarily just have one mechanical property requirement and not have a lot of variability there. Cooling method, there are different ways to apply the cooling. We saw water quench in the video that we showed. There's different types of water bath or water spray or air, but I do want to emphasize that the rate is ultimately what needs to be controlled, not the method. The method is the means to an end. So for example, a 6061 may often require water quenching, but if we're able to achieve the rate with a good air cooling, then that would be perfectly acceptable. So again, temperature control is really critical, and so is the time. Those are our main control parameters. And here's a schematic here showing a proper control. Of course, you're getting excellent billet here with minimal Mg2Si, which is really a result of their homogenizing process and the way they cool. There might be some, but it won't be anything that you can't handle. As you heat, you really won't have any significant growth. You're not having any major delays where you're staying at a elevated temperature for a long time, getting it through the preheating process. You're extruding at a sufficiently high temperature to solutionize everything. You're cooling at a rate that maintains all the mag and silicon in solution. And then when you age, we get these finely distributed particles that are optimum for strength. Conversely, if we're out of control in any one of these steps, we have problems. If we don't heat properly, or we allow really the main allowing to sit for a long time at the billet preheating temperature is really the main culprit that we have problems. We can get very large particles if we don't extrude at high enough temperature. We're not dissolving. If we're cooling too slowly, we get particles. And really, what that leads to in aging is, yeah, we'll still get some degree of strengthening, but you can see in this example, there are many fewer of the small strengthening particles in this schematic. So the strength will come up a little bit, but we will not reliably meet our properties. So I won't read all this, but again, there's this critical temperature range, 250 to 500 C. Preheating typical temperatures here, we'll just want to highlight 455 to 510 C is pretty typical for 6,000 alloys at least. We will start to grow some large particles, but in the extrusion process, if we're keeping our extrusion exit temperature high, we'll be able to absorb those particles. Cooling needs to be quick enough to absorb. I don't have it on here, but for 6063, if we come through that range in 4 to 5 minutes, that would generally be perfectly acceptable. For a 6061, for example, probably at most 2 minutes, depending on the wall thicknesses and so forth. And then aging, typical aging temperatures, there can be exceptions to this as well, but 160 to 185 C. So there's a lot in there quickly, but what I really want to emphasize at the end of this is we need to focus on the basics. Again, temperature and time, have a repeatable process. I will also say the equipment should be reliable, and we should treat the equipment with the same level of control that we treat the process. So if we need to be changing dummy blocks and aligning equipment, then that is done in a controlled way as well. Typically, the real meat of it here for those of us in production environments is we could fairly effectively drive towards better quality and having a much higher degree of throughput by just doing these very fundamental basic process improvements and making sure that our people on the floor are sticking with the plan. We have an SOP, a process for them. We're following that, and we're getting good results. I've been to many extruders over the years, and the best extruders typically probably isn't strongly enough. They always have good housekeeping. They have good discipline on their recipes and running consistently, running the product the same way every time. They have engaged their workforce. They've trained their workforce to understand the process and also know how to react when there's exceptions, and have good internal communication so that people know how they're performing and how they're doing. And really rarely is there any significant investment needed to be able to achieve that. I really want to emphasize that. There may be spot improvements, or we need to have have someone come in and align a press or something, and kind of a one-off. But really, your equipment is capable of doing much more likely than it is now, if you get back and follow these basics. And of course, financially speaking, that's what matters at the end of the day. Obviously, if we have this type of throughput improvement where we're 20 or 30, or even I've seen 50% improvement, that has a huge impact on the profitability of the company, as well as this, the future of the company and everyone employed there. Some future trends that I wanted to point out. There are really getting to be some good numerical simulation tools. That is something perhaps some of you use in some of your facilities. For example, flow software such as Qform, which is you're putting in the parameters, and it is calculating how the shape is going to come out of the press, and actually how in a given set of cooling standards, how you would expect it to deform. And you can use that in die design as well as process setup. And those simulation tools are becoming much faster, less expensive, and more accurate than they ever have been before. Automation is a big topic now and will be in the future. To me, automation is more about consistency than it is cost. Although if you have a material handler or stacker, you could potentially have fewer employees to pay. To me, the real benefit is in how consistent you are. So yes, I would encourage each one of you to design your process to meet your needs, whether or not you have such equipment. Automotive is growing, but I will caution that there is a whole nother level and a higher commitment of control that's needed to get into automotive. But that's definitely a growing sector, and it's very exciting. But to summarize here at the end of this slide, it's really focusing on good process, good business principles that's going to make a winner out of your facility now and in the future. It's not just spending money or having information. It's being out on the floor, and it's applying these basic principles. So yeah, thank you each one. I think we have some time for questions. I'm going to go ahead and stop sharing here. Yeah.
Thank you, Jonathan, for such an insightful masterclass session. And now I would like to invite my colleague, Mr. Manish Kulkarni, to facilitate the Q&A session.
Thank you, Ramya, and thank you, Jonathan, for that brilliant presentation. You really simplified the metallurgy of extrusion subject. We have received a huge amount of questions, both while registrations were being done by participants and also in the Q&A box. We will take a few questions as we are short of time. However, we will take all the unanswered questions offline. The first question, Jonathan, to you is from Ravindra Cheda from Sangli Aluminium Extrusions. And the question is, how to achieve more hardness in 6061 alloy? Jonathan.
No, that's a good question. 6061 is an alloy that to me is designed to account for some of these factors that we're talking about, and really is capable of the basic strength level even without excellent process control. But if you apply really good process control, you can get much higher properties. So I'm not sure the context of if it's a customer requirement for a higher strength level, but more than likely you will be able to meet that with a current alloy without future development by just applying these principles making sure you get feedback as you mechanically test and so forth. But you'll be able to meet 10 or 20% higher strength without a problem. And then beyond that, of course, there are opportunities for alloy development, other alloying elements. Strontium's been in the news, for example, that really can go farther beyond what we're talking about. But again, to take advantage of those, really having the basics in line is really important. So, yep, good question.
The next question is from Mr. Vishal Fulpagare from Pranav Vikas Private Limited. He's from the quality assurance function. What are the root causes of orange peel issue in extrusion point of view and raw material point of view? Jonathan?
No, very interesting question. I think most of us probably have seen orange peel, but if not, it is a surface phenomenon that really does look kind of bumpy. Whereas you had a smooth extrusion surface, now it is bumpy, kind of like an orange peel. And it is really due to subsurface grains. And when those are deformed, they sort of rotate and cause this bumpy surface. So there's really a couple factors. One, the product has, I wouldn't say abnormal, but a less than optimum or non-optimum grain structure. And then two, the deformation. Usually you would see this after stretching in the process. After cooling, you're stretching and straightening. Although with a high polar force coming out of the press, potentially that you can have that problem actually just still hot before the cooling process. That actually does relate back to what we're talking about with regards to process control as well. It's really not related to billet quality. It's you have a fixed alloy that has a certain behavior, and you're running it through a particular die that has thick walls or thin walls, and you really are controlling that grain structure by balancing the time and the billet temperature, the speed you're running, and so forth. I've seen it, for example, where there was a recipe set up and they were getting good product, and all of a sudden they began to have problems. And when they went back and looked at it, they were having mechanical issues that caused them to run slower than they normally did at the press, which then suddenly they had grain structure issues. This can be exacerbated by, by stretching as well. If, for example, you're having issues with dimensional control and you have a part that's not staying flat, it's bowing coming out of cooling, you may be pulling it more in the stretcher to try to compensate for that, and you're more likely to get grain structure. So there's that effect as well, where that stretching is being used as a, let's say, a cover for a different issue that's not really related. So, but really, again, that also comes back to good process control, making sure you're running the same way all the time, maintenance, die maintenance, everything. You have really good control of your process. So yeah, good question.
Yeah, one more question we will take. This is a very interesting question from Dilip Kumar Acharya. He's head of operations at Global Aluminium. Whether homogenizing of billets has any role for less blister formation extrusion, or degassing during casting is the only criteria. How to increase the extrusion speed in non-homogenized billet, especially 9-inch 6061, 6005A and 6082 billets? Ram, you can take this question and then we will ask Jonathan to add his pointers.
Sure, Manish. I think from a billet producer's perspective, if you look at where from it can generate, and yes, of course, there are two sources. Either it will be from the hydrogen or the porosity that is coming while casting the billet, or second, if there is a uncontrolled homogenizing process, meaning the temperature is more than what is being set up, the temperature or the time for homogenizing is exceeding this design time. Then in case one could find there is a porosity or the air bubble formation outside the billet layer, which can eventually pass on to the extrusion process as well. But I think there are more to extrusion process than to billet on these cases. So Johnny, if you'd like to please comment, elaborate on that.
Sure. Yes. Blisters are fairly common at times in extrusion, and really every single case that I can think of, I know conceptually we can have problems with billet or control and that result in blisters, but the cases that I have studied have all been related to extrusion. There are many excuse me, opportunities for air entrainment or for oil, for example, from a shear blade at the end of the billet cycle. If oil gets in the process, anything that goes in the process by definition has to come out again. So for example, we're cutting that butt off because we want that to come out. We don't want to continue to push that in the die. But if there's residual oil, or if in that shearing process, metal is pulled a little bit out of the die and there's a little air pocket that can be sealed in, that's one of the most common sources. But also, as we put the billet in, we're not just putting the billet in the container, we have air in the container. So when the container's closing, we have a billet and there's a little bit of air around, and we have to make sure we're getting that out. So a common cause of blisters as well is how we burp. I don't know if that's a common terminology in India as well, but we burp the press. We pressurize it and then we let the air out. And a part of that is just the pressure and the procedure we do that, but also the dummy block at the end of the stem, how that's functioning. If we're not in control of those, we're going to see blisters at some point. And then I should also say, if we're running two-piece or split billets, we would expect to see blisters at least sometimes as we are welding those two billets in the middle. There was another part to the question. Non-homogenized billet. My recommendation to make non-homogenized billet faster would be to homogenize it. I think unless you're running basically pure aluminum, like with a 1000 series billet, there would be no need to homogenize that. The advantages of homogenizing and evening out the cast structure prior to extrusion are by far greater than anything we can do in the extrusion process to account for that. So yeah, I would definitely always homogenize your billet, except for the pure aluminum stuff. Yeah.
There are so many questions, Jonathan. Very interesting question. I'll take this one final question from Arun Sharma and a quick answer from you. He's from Game Changer Solar. He's from the quality function. The question is, we had tested 10 samples of one heat from different cavities, and 6 passes in the mechanical properties and 4 fails in the mechanical properties. What affects the mechanical properties at the time of casting, like mold flow rate or temperature? That is a question.
Yeah. I think if you want to add anything, Ram, on the casting side, but I see this as predominantly an extrusion issue. Assuming you have the certification, the alloys to standard, and everything's controlled in the casting. Really, this relates directly back to what we're talking about, having control. If you're seeing different results, then by definition, there's been different inputs. Something is different. You may not know what it is. I don't know what it is sitting here, but we should go in with the expectation that that's what we need to figure out. Could it be that the temperature for where some of these samples was, as it was extruded, where those samples ended up was slightly different? Perhaps that could be one possibility. But to me, again, it highlights the importance of looking at the basics, understanding the temperatures and the times, and diving into it and making sure also we're not right at that in that gray area, but we're running at high enough exit temperatures, for example, that if we have a slight delay or the die's pushing hard or various normal, I'll say somewhat normal process variations, we're still able to absorb those and make excellent product.
Thank you for that crisp answer, Jonathan. Thanks for taking all the questions. And before I formally propose vote of thanks, there is a good news. We had promised that there will be a lucky draw. at the end of the webinar, and then we have at the end of the masterclass, and we have the system has chosen randomly 5 winners of the lucky draw, and a surprise gift will reach them. So please check your emails for further communication. The prize is a copy of an author-signed book written by Dr. Raghunath Mashelkar and Ravi Pandit. From Leapfrogging to Pole Vaulting is the title of the book. Creating the Magic of Radical Sustainable Transformation is the subtitle of the book. It's a wonderful book. You would enjoy reading it. The winners are, not in any particular order, alphabetical order, Mehul Chauhan of Bangkok, Prasanna Venkatesh of Boruka Extrusion, Naveen Gupta of Man Aluminium, Jason James of Malabar Extrusion, and Mr. Durga Prasanna Rath from Jindal Aluminium. Congratulations to all the winners, and stay tuned for further advice, further communication, and your address for sending the author copies, author signed copy to you of this book. I thank Jonathan for a wonderful presentation and for joining us all the way from US. I know it's a different time zone, so thank you so much again. Thank you so much, Mr. Alok Ranjan and Mr. Ram Adhikari for your initial comments and the presentation and overview of Vedanta Aluminium. And most importantly, I thank all the participants for a very active participation in this masterclass. It was truly a masterclass thanks to Jonathan and the team from Vedanta. We learned a lot about the metallurgy of extrusion. Stay tuned for more such sessions from Vedanta Aluminium. I wish you all a great weekend ahead and a great evening. Thank you and namaskar.